Hi everyone, here are your notes for lesson 2. We're going to be getting into logarithmic functions and their graphs today. So you remember last time we saw each other we were talking about exponential functions. So we had our growth and our decay functions, so now we're going to look at logarithms. And the cool thing about logarithms is they are the inverses of the exponential functions, right? And what do we know about inverses? Inverses reflect, you flip-flop your x and your y, so they reflect over that identity graph of y equals x. Okay, so here we have if your a is greater than 0 and your b is greater than 0 and b cannot equal 1, then y equals log base b of x if and only if your b to the y is equal to x. So that right there is your conversion back and forth between logs and exponentials. So the base of your log becomes the base of your exponent. The y or the output of your log becomes the exponent of your base, and then your x, your input, becomes the output of your exponential, which makes sense, right? Because you switch your input and your output for your inverses. So over here we're asked to graph both of the equations. So let's first do our exponential. So an exponential graph with our b being positive is growth, and it goes through the y-intercept of 1, 0. We know we have a horizontal asymptote at y equals 0, right? Okay, so now the line y equals x looks something like this. Y equals x. I guess I should probably label all of this. Y equals x. This is my y is equal to b to the x. And I'm going to go in a third color. So now if I reflect that red graph over the purple line, right, my 0, 1 would now become 1, 0. My horizontal asymptote is now going to become a vertical asymptote. And we'll have something that looks like that. Oops, I guess I should maybe do it more like that. Okay, so the orange is our logarithmic. So that's log base b of x. All right, so they're reflections of each other. They should be reflections across the line y equals x. Alrighty, so here are your basic properties of logarithms that you should be aware of. Note that these are also valid for base 10s and base e's. So this is going to occur when our b is positive, b cannot equal 1, and our x is greater than 0, and it will work for any real number y. So log base b of 1 is always going to be 0, right? Because anything to the 0 power is 1. Log base b of b will always be 1, because 1 to any power is going to be what? 1, right? Log base b, b to the y will be equal to y. So the easiest way I like to remember it is, here I have a base of b, here I have a base of b. Those base of b's are going to kind of cancel themselves out. So you're just left with y. Again, if you think about it as our conversion from, oops, I can't see what was up above, where we said that log base b of x equals y converts to x equals b to the y, right? So if I do b to the y, so my b to the y, isn't that equal to b to the y? Yeah, it is. It is. Third, base b of log base b of x. So again, your bases will cancel everything out, and you're left with just x. Your natural log of 1 will be 0. Your natural log of e will be 1. Natural log of e to the y would just be y. So natural logs and e's kind of cancel each other out. Right? If you don't believe me, if you do on your calculator, if you hit natural log of e to the 1, oops, to the 1, not 0, not 9, parenthesis, that gets you the 1, right? So they cancel each other out. And then the last one, if I have a base e, and then I'm taking it to an ln of x power, those e and ln's kind of cancel out, and you're just left with x. And kind of keep that in the back of your brain, because when we get into solving, you're going to have to do that. Okay, so example 1, give a reason for the following logarithmic equations. So we have log base 2 of 8 is equal to 3, y Well, because we know that my base of the log is 2. If I take that to the third power, it's equal to 8. Log base 3, square root 3 is equal to 1/2. Why? My base is 3 of my log, so make that the base of your exponent. My exponent becomes 1/2, and that is equal to the square root of 3. For C, my base is 5. 5 to the negative 2 power is equal to 1/25. D, my base is 7. 7 to the 1 power is 7. Right, so you can kind of see how the base, if you have a base here and a number attached, then it's going to be 1. And then here, my base 6 and my 6 are going to cancel each other out. So in this case, right, I don't know, they just kind of swipe out because of the rule. I would say something like, because b log base b to the x is equal to x. So it is just equal to 11. All right. So now let's look at logarithmic functions, our inverses of exponential functions, meaning our x and our y's will switch. So sometimes it's easiest to graph a logarithmic equation by first finding your order of values of the inverse of it, the exponential, and then flip it, right? Because it's easy to do exponential evaluating in our head. So for example, if I had to do 2 to the negative 2 power, so 2 to the negative 2 power is equal to 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4, right? So if I were to do the inverses of them, I would switch my x and my y. So my y was 1/4 on the exponential. So if I make x, or 1/4 be the x in the logarithmic, then the output would be negative 2. 1/2 would be negative 1. 1 would be 0. 2 would be 1. And 4 would be 2. Okay, so you just are flip-flopping the x and the y's. All right, logarithms with base 10 are called common logarithms. The subscript 10 is often dropped, so a logarithm statement with no specific base is understood to be a base 10. And on your calculator, this log button right here is log base 10. Your calculator may have, yeah, they do have an option, mine does, where it gives you an option to do a log with a base and a number. Let me get rid of this in front. Oops. Come back. Math, log base. The 83s, I don't know if they have them. So if I wanted to do 2 and then 8, right, we know that 2 to what power is 8? Well, 2 to the third power is 8. Right, so your calculator can do log bases for you, which is kind of nice. But the original log, just no base, is assumed to be 10. So for A, this would be kind of like 10 to what power is equal to 100? Well, that would be 2. So that would evaluate to 2. For B, 10 to what power is equal to the square root of 10? Well, that would be the same as 10 to what power is equal to 10 to the 1/2, right? So it would be equal to 1/2 would be our answer. So log square root 10 would be 1/2. For C, we know that's going to have to be a negative, right, to send it down. So 10 to what power is 1/1000? Or 10 to what negative power, maybe I should be putting x's in here, is equal to 1,000 over 1, right? So wouldn't that be negative 3? Yeah, negative 3. Got you there. Here we have a log base 6 of 6. Isn't that just 1? So that becomes 10 to the 1, which is just 10. All right, so now we want to use our calculator. So get your calculator out. Make sure you can do these. So if I wanted to do logs, I would hit the log of 34.5. Hit enter, I get 1.537. 5378. For B, what's B? Log of 0.43. Log 0.43, hit enter, It gets me negative 0.3665. And then log of negative 3. Uh-oh. Non-real answers. Interesting. So that makes me think. Using your answer to, so let's put, so non-real solution. So that makes me think, what can we generalize about logarithm functions? The domain has to be greater than 0. Can it be 0? Oh, let's quickly do a log of 0. Will it ever hit 0? Hopefully you're already thinking the answer. Why won't it ever be 0? Because isn't that an asymptote? Yes, it is. So our domain has to be positive, right? So our domain is all numbers, so it's from 0, not including 0, so exclusive on the 0 to infinity. All right, so now let's go ahead and solve logarithmic equations. All right, so to solve an exponential equation, we change it to a logarithmic equation. To solve a logarithmic equation, we change it to an exponential equation. So you do the inverses of them, which is kind of cool. Because to solve an addition equation, you subtract, you do the inverse, right? To solve a multiplication equation, you do the inverse, you divide. To solve a square root equation, you square it. To solve a squared equation, you square root it, right? You do the inverses of them to solve them out. So we're going to do the same thing here. So here we have log of x is equal to 3. Well, my base is a 10, so I'm going to turn this into an exponential form. So 10 to the third is equal to x. Well, that's easy to solve. That's just 1 with 3 zeros. So 1,000 is equal to x. I make it fancy and put it in set notation. That makes me feel cool when I put it in set notation. How about you? For part B, my base is 2, so I'm going to do 2 to the 5th is equal to x. 2 to the 5th is 32. I feel like we just did that today in class, which really would be 3 weeks ago. But really, it's today in my brain. Let's make it fancy. 32, the set of 32. All right, so let's bring some e into our life. So your natural logarithms, also known as ln, just have a base of e. And remember, e is 2.718, blah, 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 right? So if we were, instead of writing log base e, we write ln. And your calculator does have the natural log button on it right here, right? So we can do the ln. All right, so evaluate the following logarithmic and exponential equations. So we have the natural log of the square root of e. So that's kind of like saying that, so my base is e, right? So e to what power is equal to the square root of e, or e to what power is equal to e to the 1/2? Well, x would have to equal 1/2, right? So if we think about this way, natural log of e to the 1/2. Your natural log and e's cancel out, and you're just left with the 1/2. So any ideas what this one would be? Why didn't that just cancel out and get you to 5? Yes. This would just cancel out and get you to 4. I mean, we could write it out, make it more complicated, but I don't know why. We could make this e to what power is equal to e to the 5th. Well, since my bases are the same, x would have to be 5. Over here at c, it would be kind of like, to convert it, it would be the natural log, or let's write it this way, the log of base e of something is equal to the natural log of, I don't know why my natural log turned into an h, natural log of 4. Well, this is the natural log of x is equal to the natural log of 4, so x would have to equal 4 to get both sides the same. So just remember they cancel each other out. That's probably the easiest and simplest way to remember it. Calculator, here we go. Speed, ln 2.23.5 is 3.157. Write it down. ln of 0.48 is negative 0.733969. Write it down. My phone is talking to me. I guess it got really excited as I was getting. So any ideas what's going to happen here? Natural log of -5? Yep, you guessed it. Non-real answer. So no non-real solution. Non-real solution doesn't exist. Why doesn't it exist? Because our domain for any logarithmic function, even if it has a base of e, is from 0 to infinity. Oh, what is going on right now? My Siri is doing something really crazy on my phone right now. Did I say a word that sounded like Siri? All right, example number 7. We've got the natural log of e to the 7. So again, your natural log and e are cancel out and you're just left with 7. I could just... All right, I need to stop Siri from talking. Okay, I'm back. I think it was Alexa talking to me. I never use Alexa in my life. Again, we can make it more complicated and can do something like e to the 7th power is equal to e to the x, or sorry, e to the x power is equal to e to the 7th. Well, x would have to equal 7. For b, we could turn this into a logarithmic equation. So log base e of x is equal to ln of 81. It's equal to my exponent. My exponent goes over here. Well, that's the ln of x is equal to the ln of 81. So what does my x need to equal to make both sides equal? 81. They just cancel each other out. C, cancel them. Leaves you with the square root of 9x. Well, the square root of 9 is 3, so that's 3 square roots of x. And then for D, isn't that the same as ln of e to the -5? So -5? Yeah. Okay, so don't overcomplicate them. They're pretty simple. Pretty simple stuff. All right, so let's go ahead and graph logarithmic functions. So let's graph a basic ln of x graph. So we know that a natural log or a logarithmic function has a vertical asymptote at x equals 0, right? Because exponential has a horizontal, so logarithmic is going to have a vertical. My y-intercept now becomes my x-intercept at 1, 0, and it's going to go something like this, right? So this vertical is at x, vertical asymptote's at x equals 0. So let's do a little bit of analysis on this. So my domain is now going to be from 0 to infinity, which that was our range for exponentials, right? My range is all real numbers, which was my domain for exponentials. And remember, we flip-flop domain and range for inverses. This graph is still continuous. There's no extrema. Let's see. It's unbounded above or below, so there is no boundedness above or below. We got a vertical asymptote at x equals 0. And let's discuss the end behavior. So the limit as x approaches -infinity of f of x is getting closer and closer to 0. Oh, no. It's going down to -infinity, right? No, and behavior keeps going down. So it keeps going down. Right? Yes, it keeps getting smaller and smaller. It's not going to stop. And my behavior, I had to think for a second, as x approaches positive infinity of f of x is positive infinity. Still thinking about that negative infinity. It is negative infinity, right? Because it would be 0 if it was getting closer and closer to 0. Yes, it's going to negative infinity. It's going to keep getting lower and lower. All right, let's go ahead and talk about transformations. Example 7, describe how to transform the graph. All right, so we got an x plus 2. The plus 2 is happening to the x. So that means we're going to be going to the left 2 units. So my original 0, 1 is going to go to 0, 0, and then over here to -1, 0. My horizontal asymptote that was here is going to move over 2 units. So now my horizontal asymptote is at x equals -2. And then let's just sketch our graph. Oh, do I have a y-intercept? Can we get a y-intercept? When it's 0, it's going to be the natural log of 2. Just some funky probably number. Natural log of 2 is, nope, I don't want to store it. Natural log of 2, 0.6931. So 0.6931. All right, so here's my graph. Something like that. Okay, so for part B, let's figure out what's happening here. I got a negative in front of my x, so that means we're going to reflect over the y-axis. So that means my original x-intercept at 1, 0 is going to reflect over to here. So that's where my new point's located. If I were to take out a negative out of this, that would make it positive x minus 3. So that means we're going to move to the right 3 units. So now I'm going to move that dot right 3 units. So 1, 2, 3. So now I'm at 2, 0. And we know instead of this, we're going to be doing this, right? Because I'm reflecting it. So now I got to figure out where my asymptote is. So my vertical asymptote is shifting to the right 3 units. So that's going to put me at x equals 3. So dot it down. That was not very straight. And then up, I could find my y-intercept. If I plug in 0, then it's the natural log of 3. What's the natural log of 3? Natural log of 3 is 1.09. So 1.1-ish. 1.1-ish. There it is. Hopefully yours looks a lot better than mine. See? Now we got a log graph. Just means it's a base 10. The shape's still going to look the same, well, except for the 3. That's going to change things a little bit. We have a 3 out in front. So that means we're going to have a stretch factor by 3. It's a vertical stretch factor by 3. My vertical asymptote's not moving, so that's going to stay still at x equals 0. So there it is. 1, 0, my y-intercept, or my x-intercept is not changing. So now let's get another point. If I do 10, the reason why I'm picking 10 is because I have a base 10, and I know that anything log base 10 of 10 is 1. So on my graph, I know I'm going to have something like 10, 3. Okay, and the last one, we've got 1 plus the log of x, which is the same as the log of x plus 1, right? So that's just going to move us up 1 unit, which my vertical asymptote still is going to be okay, still at x equals 0. So instead of 1, 0, we're going to be at 1, 1. And it's going to look something like that. So another number ordered pair on there. If I plugged in 10, wouldn't that give me an output of 11? Because 10 log of 10 is 1. 1 plus 1 is 11. Just food for thought. Food for thought, why not? All right, that's your notes. Hopefully that's pretty simple.